Hello class and welcome back to Chemistry in the Physical Setting. This is Unit 4, Chemical Bonding, and Lesson 1, Bond Energy and Electronegativity. And today's major understanding is that when a bond is broken, energy is absorbed, and when a bond is formed, energy is released. And also that electronegativity indicates how strongly an atom of an element attracts electrons in a chemical bond. We'll begin with bond energy, and basically a bond is a stabilization of two atoms by sharing or transferring electrons. And to fully understand bond energy and what a bond is, we should first analyze elements that do not commonly form bonds. And those are the noble gases, which are group 18 elements, and they're relatively unreactive, and that's due to their stable electron configurations and low potential energies. So they're extremely stable. So if we look at an example like helium-4, where we have yellow spheres equaling electrons, red spheres equaling protons, and blue spheres equaling neutrons. We'll see helium-4. Helium has an atomic number 2, so it has 2 protons. Since it's helium-4, it has 4 subatomic particles contained within the nucleus, so 2 protons and 2 neutrons, and it has 2 electrons in the first energy level. And this is the maximum number of electrons that can fit in the first quantum energy level. So this outer energy level is completely full. And if we look at another noble gas like neon-19, neon has 10 protons. Since it's neon-19, it has 9 neutrons and 10 electrons. And so again, the first energy level is completely filled when 2 electrons are contained within the first energy level. And the second energy level is filled when it contains 8 electrons. So again, the outer electron energy level or valence energy level for both of these atoms is completely filled. You can't add any more electrons to it. Okay, and so if we analyze the electron configurations of all noble gases, we'll see that this outer energy level is always filled. So argon has 8 valence electrons, krypton has 8 valence electrons, xenon has 8 valence electrons, and radon has 8 valence electrons. And so noble gases do not bond with themselves or any other atoms and are commonly observed as monatomic gases in nature, which means basically they are completely on their own by themselves in nature, unbonded. And this is due to the fact that their valence electron energy level is completely filled. So they do not require any more electrons in order to fill their outer energy levels. And so you may have noted from earlier that the magic number for stability in electron configuration is having 8 valence electrons in the outer energy level, except for helium. Helium only has 2 in outer energy level because that's the maximum electrons that can fill that first principal energy level. And so since mostly all other atoms are stable when they contain 8 valence electrons, we call this rule the octet rule, which is that atoms of other than noble gases have unfilled valence energy levels, and as a result, they're unstable. So the 2 atoms we're currently looking at right here, sodium and fluorine, both of these atoms are unstable. They do not have 8 valence electrons in their outer energy level. So if you look at sodium, sodium currently only has 1 electron in its outer energy level. And if we look at fluorine, fluorine currently has 7 electrons in its outer energy level. And so atoms gain stability by either transferring or sharing electrons to achieve a more stable electron configuration. So if you look at the formation of a metal ion or the formation of a sodium ion in particular, we'll see that sodium has to either gain 7 more electrons in its outer energy level to obtain a stable 8 electron configuration, or it has to lose 1. And the easier path energy-wise would be to just lose 1 valence electron. And so sodium loses its 1 outer electron, and as a result, it now has 8 valence electrons in its outer energy level. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 valence electrons in the outer energy level. And so this has now become a sodium ion, and the sodium ion now is more stable than the original atom. Okay, fluorine, on the other hand, is a nonmetal, And so the easiest path for fluorine to obtain stability is to just gain one more electron. It currently has 7 valence electrons, so by gaining one more electron, it's now able to have 8 valence electrons. So this red dot represents the electronic gain. So if we count these up, 1, 2, 3, 4, 5, 6, 7, 8, fluorine now has 8 valence electrons. And this is a common pattern where we have metals where they generally will lose electrons in order to gain a stable 8 electron valence configuration, and nonmetals will generally gain electrons in order to obtain this 8 valence electron configuration. And so the new stable configuration generally results in 8 valence electrons, and this is why this is called the octet rule. Octet for 8, or 8 rule. Due to the fact that when an atom gains 8 electrons, it becomes stable, and as a result, it has a lower potential energy, when we talk about forming a bond, formation of a bond generally results in the release of energy, and this is due to the stability of the atoms. So if we have 2 fluorine atoms forming a covalent bond, formation of a covalent bond, these 2 atoms are going to come together and they're going to share 2 electrons in what we call a single bond. And so now if you look at these atoms, they both have 8 valence electrons, and it's due to the fact that they're sharing these 2. Since these 2 atoms now have increased in stability, they therefore lose potential energy, and that energy is released into the surroundings. So we have this release of energy when a bond is formed. And the opposite is true for when breaking a bond. So in order to break a bond, since we're creating a more unstable situation for both atoms involved in the bond, there's going to be an increase in potential energy between those 2 atoms and an increase in instability, or a decrease in stability. So absorption of energy is required for the breaking of a bond. And again, this is due to that decreased stability of atoms. So in order for these atoms now to have less than 8 electrons, since they want 8 electrons, there's energy is going to be required to remove or separate the 2 atoms and break the bond. And so once a bond is formed, there's different, each atom has a different ability to attract the electrons that they are now sharing. So electronegativity is a measure of the atom's attraction for a bonded pair of electrons. The measurement of how much an atom in a bond wants the electrons that it's sharing. And so if we look at a hydrogen fluoride bond, we'll find that the greater the electronegativity, the greater the attraction for electrons. So when evaluating a bond between hydrogen and fluorine, we'll find that the electrons will exist on fluorine more than they will on around the hydrogen atom. So due to the fact that fluorine has greater electronegativity, it means that the electrons are going to exist around fluorine more. So we'll have this uneven electron distribution, that's what this red cloud is trying to represent. That we have the electrons will be in this region more than in this region around the hydrogen atom. And so this is due to the fact that fluorine has a higher electronegativity value. So fluorine has an electronegativity value of 4.0 and hydrogen has an electronegativity value of 2.2. And to find these values, all you have to do is look up all the electronegativity values contained within Table S of the New York State Chemistry Reference Tables. And basically, the greater the electronegativity value, the stronger the attraction for the electrons contained within the bond. And so that's the end of lesson number 1. Look forward to lesson number 2, types of chemical bonds, and I will see you in class tomorrow.